Okay, let's look at Math Breeze. I didn't assign anything new. We do have things due, let's see, Monday, okay, and tomorrow, a Weatherly assignment tomorrow, and Monday we have 103, 104. Over the weekend, I'll create some more. I have to create some more problem sets. Let's see, we're up to, I want to create problem sets for 105, 106, and 108. Today we're going to look at 108. Okay, so we have to catch up with that. Most people got their tests back. Yeah, Monday evening, right? It's always whenever I have assignments due, they're always due at midnight. Most people got their tests back, but I still have about 8 more to grade, so I'll be grading them and sending them to you. All right. Okay, so in chapter 106, we were looking at a test called the ratio test. All right, and if the ratio test is true, then we have absolute convergence. All right, so let me just remind you what the ratio test looks like. All right, so we want to know if this thing converges. Okay, so then we form the ratio of the absolute value of a n plus 1 divided by the term before it. Okay, so if this goes to a limit, and if that limit is less than 1, then that implies absolute convergence. If this is greater than 1, then that means divergence. But this is the important part of the ratio test, so that I put right here. So basically what this tells us is that this series is similar to a geometric series. A geometric series has a ratio of a term divided by the term before it equal to r, where r is less than 1 if we have convergence. All right, geometric series, this division would be equal r. If r is less than 1, we have convergence. If r is greater than or equal to 1, we have divergence. Now for the ratio test, basically we form this ratio, and as n goes to infinity, a term divided by the term before it is very close to r, where r is less than 1. That would be something that passes the ratio test. All right, so it's similar to a geometric series when n is large. All right, so here, let's look at this example, and we'll see that when n is large, this factor takes over. This factor n over here is large, but this one, 2/3 to the n, will be very, very small, and this n, the fact that this n is multiplying, won't be that significant. So let's try the ratio test. This is a typical ratio test, a series, or a typical series where the ratio test can be applied. So let's try it. All right, so now we're doing, I won't use absolute values here because everything is positive. All right, so we're just looking at the n plus first term divided by the nth term. Okay, so we can just divide here. So here we have n over n plus 1 over n. And here we have 2/3. And now we're ready to take the limit as n goes to infinity. Or maybe first we'll divide over here. All right, before we take that limit, divide n into n, and we have 1 plus 1 over n times 2/3. So as n goes to infinity, this goes to 1, 1 over n goes to 0, and the whole thing goes to 2/3. The limit is 2/3. Okay. That's less than 1. So that means we do have convergence. You also, actually, you have absolute convergence. In this case, the terms are all positive, so that's not really, this is absolute convergence. It's the same as convergence in this case because all these are positive. Okay, let's look at this one. You recognize when the ratio test could be used. Very often the problems contain n factorial, and they contain something like 2 to the n, 3 to the n. All right. So those are typical problems where the ratio test is used. And usually you have factors. You don't have things added together. Like, let me just show you on the side here. If we had something like this, 1 over 2 to the n plus 3 to the n, that's what I mean by terms added, then I don't think the ratio test would be good on this series, because if we do I think it's not a natural one for the ratio test. It might work, it might not, I'm not sure, okay? But not natural. If it was 2 to the n times 3 to the n, things multiplied together, that looks more like a ratio test possibility because you end up with a lot of canceling. Okay, so things multiplied together, not added in the, factors multiplied in the numerator and denominator, those are usually candidates for ratio test. So let's try this here. So we're looking at an plus 1 divided by an. But okay, if we just, you should also have a feel for whether or not this will converge or diverge. Look what's going on in the numerator. We have a bunch of 2's multiplied together. All right, let's look at, let's say, the 5th term. So we have 2 to the 5th, so we have 5 2's. Just so you have a feeling for what's going on. And here we have 5 factorial, so that's 5, 4, 3, 2, 1. We see the denominators definitely look bigger than the numerators. Here we have a bunch of 2's. Here we have n factorial, so these are getting bigger and bigger. When n goes to infinity, we're going to have very big numbers down here. So, and on top, we just have a bunch of 2's. All right, smaller numbers. It does look to me like this will converge. Okay, so let's write this out. And we ignore the minus 1 to the n because we're talking about absolute value. All right, so here we have 2n plus 1. And here we have n plus 1 factorial. And here we have 2n, n factorial. Okay, I'm just going to do the reciprocal of the denominator. And rearrange so that we have, a lot of canceling. Usually you have a lot of canceling with the ratio test. So we'll rearrange this. Put the powers of 2 in one fraction. And usually you get a lot of canceling. Here we just have the number 2. And here we have n factorial divided by n plus 1 factorial. So we have this starts with n times n minus 1 all the way down. And this one starts with n plus 1, n minus 1, and down. Okay. So you see, we get all this canceling. So we're left with 2 over n plus 1. All right, so now just take the limit, n goes to infinity. And we have 0. All right, so that means we do have, so we have 0, that's equal to our r, which is less than 1. So we do have absolute convergence. by the ratio tests. Okay. So in other words, this denominator is going to infinity much faster than this numerator. So basically, it's like a race. You can think of it, n factorial is winning by a lot. All right, that's what this shows us. All right, let's look at another example. All right, now we're going to let's look at some examples where we're going to use any test at all. Okay, I'm just going to write these down. And really, the hard part is just identifying the test, or really what you have to get good at is identifying which test to use. It's sort of similar to in Math 16, we had to identify which integration technique works. So here we have to identify which test. So I think we won't even do all of these. I think I'm just going to write them down and we'll identify the test rather than actually do the integration, rather than actually do the test. I think that's a better exercise. I'll just put a bunch down. Okay, let's look at those. All right, so it says use any test. Does somebody want to tell me what could be used here in number 1? Anyone see what could be used here? First of all, let's write this. See, n times n to the 1/2. Let's write it as just multiply n times n to the 1/2. We have n to the 3/2. Okay, so right now, what do we have? How can we, does this one converge or diverge? Anyone know? Anyone tell me? Converge or diverge? What do you think? Okay, so you should know by now that, right, exactly, this power is greater than 1, 3/2 is greater than 1. Okay, good, so that means converge. So this one converges because it's what we call a p-series. And p is greater than 1. Okay, so we have the sum 1 over n to the p that converges if p greater than 1. Okay, so p-test. Let me call it p-test. I'm not sure if it's called p-series. It might be, but I'm not sure. So let me call it p-test. So this is basically the p-test. And it comes from the integral test, the integral p-test. All right. If you integrate this from 1 to infinity, integrate 1 over x to the p from 1 to infinity, it converges if p is greater than 1. So this right away converges by the p-test. Okay, what would we do here for this one? I see two things we could do. All right, any ideas? First of all, tell me if you think this converges or diverges. Right, exactly. We can compare to 1 over n. Okay, that's all right. So Elizaveta suggested it's similar to 1 over n. So we could do a limit comparison. Okay, with see if we take the highest power on top divided by the highest power on bottom, we can ignore the 2. So this is similar to n over n squared. So we can, I'm going to write similar to. Okay, so you can do a limit comparison. And you would get, since this diverges by the p-test, you would get divergence. All right. Okay, what about this one? What test do you think we should do here? Any idea? Okay, well, this one, we know how to integrate this. See, you should recognize that this is not difficult to integrate. Okay, so Elizabeth has said L'Hopital. All right, L'Hopital might show that, well, we don't really need L'Hopital here. These do go to 0. All right, we definitely need that. We definitely need that these terms go to 0. Otherwise, there's no hope that something converges. All right, so these do go to 0, so that's okay. All right, but the question is, does it go to 0 fast enough? Does it die down fast enough? We know 1 over n does not. 1 over n squared does. This is in between 1 over n and 1 over n squared. We have n times something else. Is it big enough? Okay, is this denominator getting big enough, getting big fast enough? Or is 1 over this denominator getting small fast enough? That's what we're asking. Okay, well, this does look like something that we've integrated in the past. So if we integrate this from 2 to infinity, this is equal to, I think we did this one. Just stick that 1 over x on top, and ln x stay in the denominator. This is of the form of function and its derivative on top. So that's what we call the log integral. So this is equal to the log of whatever the denominator is. In this case, the denominator is log x, log x. And if we evaluate from 2 to infinity, if we substitute into infinity or look at this as x goes to infinity, it does go to infinity. Okay. Since log x goes to infinity, so we're looking at basically log infinity, which is infinity. Minus log 2, but anyway, that's not significant because the first term goes to infinity. So this diverges. See, by just looking at this, you can't really tell if it converges or diverges. You really have to do the integral test because, you can't really use a p-test over here. Like I said, this is in between 1 over n and 1 over n squared. But it turns out it's not, these do not get small, or the denominator doesn't get big fast enough. Let's look at the denominator. N squared would be good. N is too small. This is in between, still too small. N times ln n still does not get big fast enough for that to converge. That's what we see over there. Okay, this one, what test do you think we should use here? What do you think? We did one like this, right? And just right here in the beginning. This was very similar. This first one was very similar. All right. This is a typical ratio test. Remember I told you have things multiplied in the numerator and things multiplied in the denominator, not terms added. That's typical for a ratio test. So when looking at this, you should recognize, if you do a lot of them, you'll recognize that we should do the ratio test here. And I think we will get convergence because n factorial compared to 7 to the n factorial is getting very big. 7 to the n, that's just staying at 7, but these n's are being multiplied out and the n's are getting big. All right, let's if you want, we'll do this ratio test. Okay, let me move this one down and we'll finish number 4. Okay, so let's do number 4. It's positive, so I'm not going to use absolute values. We're just forming this ratio. Okay, so that's 7 to the n plus 1. That's a to the n plus 1. And here's a to the n. So we're going to get a lot of canceling or simplifying. Okay, I'm just going to take the reciprocal of the denominator. And now let's put things together that cancel. All right. Okay. Or maybe we can even do it right here. All right. When we reduce n plus 1, that's the first term in n plus 1 factorial. So here we'll be left with n factorial, that reduction. And something in here too, we have n, and cancel out the first n in n factorial, and then we're left with the rest of them, which is n minus 1 factorial. And then we have 7 to the n and 7 to the n plus 1, so we're just left with 7 on top. All right, so let's see, what do we have left with on top? We have 7 times n minus 1 factorial in the numerator after the canceling. And then the denominator, we have n factorial. So now we have some canceling right here that we can do. Okay, n minus 1 factorial and n factorial. N factorial is n times n minus 1 factorial. So we're just left with the n, and the n that's the first factor here. Okay, so finally we get 7 over n, which goes to 0. So that's our r, all right? And we have r is less than 1. Okay, so that implies we do have convergence. Okay, now this one, we have the cosine n on top over 2 to the n. So maybe we should just compare it. We could compare it with the sum 1 over 2 to the n. Okay, so we should realize, first of all, that cosine n is between, this is between minus 1 and 1. All right. So if we take, let's say we take the absolute value of this. So first of all, let's use the following fact that we mentioned, but I didn't emphasize it when we looked at absolute convergence. And one important theorem in that chapter is that if you have positive and negative terms, if you take the absolute value, this sum is going to be bigger than just the sum a to the n. So if this one converges, then so does this one. Because here these are all positive. These could be positive and negative. So this will definitely be smaller. So if this one converges, then this smaller one will as well. Okay. So in this case, we can use that here. Let's look at the absolute value. This sum, if we take the absolute value, and we can compare it with, we can do a direct comparison. Well, let's take one term at a time, not the whole sum. Let's just do a direct comparison. This is less than this, because the cosine n in absolute value is at most 1. So this is less than or equal to this. All right, and we know that this converges. That's a geometric series where r is 1/2, which is less than 1. You know, just a regular geometric series. So we know that one converges. That means so does this one. Okay, so if the absolute value converges, that means if we remove the absolute value, that also converges. So when you look at this, you should realize that, first of all, it's very important to realize that cosine is between -1 and 1. Okay, and so then you should realize that this thing converges, because if this is between -1 and 1, then you could compare it to 1 over 2 to the n. You know, especially it's comparable when you take the absolute value. All right, you get numbers up here that are less than or equal to 1, so certainly you can compare to 1 over 2 to the n. All right, and the sum 1 over 2 to the n converges. So this one is actually smaller because these numerators are smaller in general, because these numerators are less than or equal to 1. All right, so see, these numerators here are less than or equal to 1. So they're in general smaller than these, less than or equal to these terms. So this one converges, so that one does as well. All right, we'll practice some more of these another time. But this is a good exercise to take some and just try to recognize which method to use. Like I said, it's very similar to recognizing which integration technique to use. All right, maybe I'll write myself a note, try to create some sort of exercise sheet on recognizing which method. I'm just writing a note. To recognize method. Okay. All right, so we're going to go on and look at the next section. And really, one of the reasons why we were looking at series is because we're interested in a type of series that's very convenient to mathematically, and I'll show you what I mean now. Okay, so this is called Chapter 107. It's called Taylor polynomials. And approximations. Okay, so here's the introduction. Let's say we have just an ordinary polynomial. Okay. So we say that this is algebraic. An algebraic function. An algebraic function is composed of, let's say, with one variable. An algebraic function with one variable. It has a variable and it has operations like multiplication. Here we're multiplying, exponentiation, addition, subtraction, and square roots. That would be included in exponentiation. So those are algebraic. Basically, f of x is equal to some formula in x. And we can just substitute in and figure out what f of x is equal to for various values. Okay, where Whereas we have other functions like y equals sine x. Okay, these aren't algebraic. Y equal e to the x, y equal ln x. To get values of these functions, we don't have this type of formula that we can substitute into. We rely on either our calculator, or years ago we had tables where we looked up values for these functions. All right, so these are not algebraic. These are called transcendental. Okay. Okay, so what do we want? So our goal is to obtain, it would be nice if we had a formula, let's say for e to the x. So let's say we can obtain an algebraic expression to approximate or to equal, maybe actually to equal y equal e to the x, okay, and others as well, and other functions. All right, so it would be nice if we had basically a formula for e to the x. Let's think of it like that. Okay, so first we said obtain an algebraic expression that approximates y equal e to the x. So we're going to see that we can get a polynomial to approximate y equal e to the x. Now, what degree is the polynomial? Well, if we say choose a polynomial of degree 4, we get a pretty good approximation. If we choose a polynomial of degree 100, we get a much better approximation. So the more terms that we have, the better the approximation. Now, if we want an algebraic expression that actually equals, that actually is equal to y equal e to the x, we need an infinite polynomial. And that's a series, basically. So that's, we're going to have a series, it's called the Taylor series, that will be a formula for y equal e to the x. It's an infinite series, and if you substitute in, you get the values of y equal e to the x. Okay. All right, so let's look at the first. So this, how are we going to obtain this? A polynomial that approximates y equal e to the x, or any function. All right, so here's our first picture. So let's look at this picture. So we have, let's say, a function y equal f of x. Okay, let's say, I'm just going to draw a generic function. Let's say this is f of x, and we want some sort of polynomial that approximates f of x. So what one can do is say, well, okay, if I draw a tangent line, that doesn't really approximate f of x very well, but right over here, very close, it's a good approximation near that point, wherever the tangent line is touching. Okay, so near x0, we have a nice approximation. Okay, what is this tangent line? We'll call it our first polynomial approximation, p1 of x. So just using the equation of a line, it's equal to f of x0 plus the slope f prime of x0 times x minus x0. All right, so here we're just using, I'll just put in parentheses, we're using the equation of the line, y minus y0 equal m, x minus x0. That's what we're using here, the equation of a line, where I just put the y0 on the other side. This is the f of x0. This is f prime. And for y, that's the p1 of x. So we're just using the formula for the equation of a line. All right, and that's our first polynomial. So we're saying, okay, that's our first approximation of f of x. And it'll be a good approximation very close to x0, and then it gets bad over here and here. It starts getting bad very quickly. Now, what does p1 of x have in common with f of x? So let's say, notice that if we take the derivative of p1, well, notice the following first. First, we definitely have that p1 of x0 is equal to f of x0. At least at x0, the two are the same. They both go through this point. All right, they're both equal to whatever this is, y0. So we have that. We want this to be close to this. So at least they are equal over here. Another thing we can notice, and this is very important, the derivative at x0 is equal to the derivative of f at x0. Right. Look at the derivative of this. This is a constant that drops out. All right, you're just left with this. This is what you'll be left with, f prime of x0, when you take the derivative of p1. And okay, so the first derivatives are equal at x0. Okay, so that gives us a fit that's only good very close to x0. And the reason why it's a good fit is, well, of course they're equal and the derivatives are the same. This gives us a good fit. So you might say, well, why don't we take a polynomial that has that's equal to our function at x0, who's with equal first derivatives at x0 and equal second derivatives. Why don't we go further? Include the second derivative as well, another polynomial, and that'll be a polynomial actually of degree 2. So that's the general idea. The more matching we have at higher order derivatives, the better this thing is going to fit. All right, that's the whole idea. Okay, so how can we get a polynomial that matches? So here's the problem. So how do we build and I'm going to call it like a custom-made polynomial for f of x that has let's say, we definitely want, well, let me put p first. We definitely want, here, I'll put it first. We definitely want we want them to be equal at x0. We're only concentrating on one point. All right, we want the first derivative to be the same. So that we have a nice tight fit. But let's get some more also. Maybe the second derivative can be the same. And maybe the third. Once we get into third derivatives, we'll just put a little parentheses 3 here. So we're only concentrating on close to x0. What happens further on, we can't solve that at this point. So let's get a lot of them. In other words, get a polynomial where it's going to be a higher degree polynomial. It's actually a polynomial of degree n, where we have n matching derivatives. We have the function matching and n matching derivatives, lots of matching derivatives. So that'll be a nice fit. So if we graph that polynomial, it's going to be much better than this line. It's going to hug the curve nicely around here, and then it's going to go off. But near x0, it'll be a tight fit. All right, so to see what to do, let's look at this following little example. Okay. All right, let's say here's a polynomial. And I'm going to do a polynomial of degree 4, a plus bx plus cx squared plus dx cubed plus ex to the fourth. And what I want to do is see what happens when we take derivatives and substitute in 0. This time, our x0 will be 0, all right? So what happens when we take derivatives and substitute in 0? So that's what we're going to do. Let me just write that down. We want to find, okay, let's say p of 0, the first derivative at 0, the second derivative at 0, third, and fourth. Okay. All right, so let's find that. So first of all, p of 0, that's a. Everything drops out. Let's do, let me skip a little space here. Okay. First derivative. Okay, that drops out. We have b plus 2cx plus 3dx. Sorry, that's 2cx plus 3dx squared plus 4ex cubed. Okay. And now put in 0, and what's left? Just the b. Everything else. So if you do the first derivative, the first derivative is just going to be that b over there. All right, now let's do the second derivative. Okay, here's the first, do the second derivative. Okay, that drops out. We have 2c, okay, plus. Okay, so the question is, why do we stop at 4? Just for this example, all right, just to see practice what happens when we take derivatives of polynomials. All right, so here, second derivative, okay, so we have 2c, and what happens here? We have 3 times 2, I'm bringing that 2 down, dx, and here we have 4 times 3, ex squared. And now let's substitute in 0, and we just have that 2c that remains. All right, now I want to do the third. Okay, that drops out. Okay, for the third, we have 3 times 2 times d. And then here, 4 times 3 times 2 ex. Okay, now put in the 0. And we're just left with 3 times 2 times d. Okay. And one last one, we're going to do p4. Okay, so look at the fourth degree, take the derivative one more time, that drops out, and we just have 4 times 3 times 2 times e. And if we substitute in 0, we get the same thing. Okay, so the main point here, let's just look at what's going on. All right, the value of 0 just depended on the constant. All right, the first derivative, it had something to do with the coefficient of x1. All right, actually it was equal to the coefficient of x1. The second derivative, when you substitute in 0, that has something to do with the coefficient of x2. All right, it's 2 times the coefficient of x2. All right, the third derivative, it has to do with the coefficient. See, d is the coefficient of x3. It's actually 3 times 2 times the coefficient of x3. And look at the coefficient of x4 is e. And the fourth derivative, when we substitute in 0, we have something that has to do with e. We took the derivative 4 times, so we got 4 times 3 times 2 times e. You see here we only took the derivative twice, so we got 2 times that coefficient. Here we took the derivative 3 times. From bringing down all those exponents, we got 3 times 2 times that coefficient of x cubed. And here 4 times, so we got 4 times 3 times 2 times the coefficient of x to the fourth. So when we take these derivatives and substitute in 0, if we take the fourth derivative, we're going to, and substitute in 0, we're just going to get something times, we're going to get, actually, this is 4 factorial times the coefficient of x to the fourth. All right, so that's what remains. Now let's just generalize this. In the next example, we'll generalize it. All right, so this is, let me see, what example was this? Okay, I'll just put example here. So in the next example, we're just going to generalize this. Okay, so let's say this time we have a polynomial. First term a0, second one a1x, a2x squared, up to n. We take n derivatives and substitute in 0. We're going to have something, then something times a to the n, and what we're left with is n times n minus 1 all the way down, to times 2 times 1. I'll leave out the 1. That's what we're left with. From all the pulling down of exponents each time we took the derivative, we took n derivatives, we're left with, this is from taking all those derivatives, times a to the n. All right, so that's what happens when we take n derivatives and substitute in 0. All right. Okay, so if we want, how should we choose our polynomial so that I want the nth derivative to match up? I want this to equal to fn of 0. All right, this is equal to, actually, maybe first I should write this as, well, let me just write it above. This is n factorial, just a shorter way of writing this. N factorial times a to the n, right? That's what this is equal to. All right, so basically it's easy now to see what our polynomial should be. So we want f sub n of 0 to match up, to be equal to Pn 0. We want our functions, our derivative of our function, to match the derivative of the polynomial. So I'm just going to put these equal to one another. So we want this to equal n factorial times a to the n. All right, so how should we choose a to the n? A to the n should be equal to this. Okay. In other words, okay, so this is what we're saying. If this is our polynomial, we'll make it equal to f sub 0 plus f prime, f1 of 0 over 1 factorial, which is 1, times x to the 1, plus second derivative, 2 factorial, which is the same as 2 times 1. Okay. We'll make this the third coefficient, and we'll keep doing this, times x cubed. And the last one I'll put over here. That polynomial, if that's our polynomial, then all these derivatives will match. So we have our, what I called our custom-made polynomial. that has matching derivatives, okay, for k less than or equal to n, all right? So all the derivatives up to n, also the first value matches as well. All right, so that's our custom-made polynomial. Let's do an example. We'll just do one example. Let's say we have e to the x. This is the easiest one because the derivatives of e to the x, the derivative of e to the x is equal to e to the x. So here we have to take all these derivatives, but in the case of e to the x, it's very simple. All the derivatives of e to the x are equal to e to the x. So that's very simple. All right. So here, if we take f of x equal to e to the x, we have f prime of x, they're all equal, f2, second derivative, all the derivatives are equal to e to the x. Okay, also, when we substitute in 0 for any of these, okay, or let's just say, okay, let's say fk, any derivative is equal to e to the x, right? So what happens when we substitute in 0? All right, so now let's form our polynomial. Just look at this line over here. We're forming our polynomial. F of 0, that's e to the 0. That's 1. This is, again, e to the 0, which is 1. Okay, this is 1 again. They're all 1. Okay, this one, again, this is 1 again. So this polynomial approximates e to the x near x equals 0. Okay, because we're matching derivatives, not all over. We're only matching derivatives at x equals 0. All right, we're plugging in x equals 0 here. So we're matching derivatives at x equals 0. So this polynomial, so e to the x has a very simple polynomial that approximates e to the x. All right, it's a very simple polynomial because these are all 1s on top. All right, now let me just show you a graph, a little diagram that I prepared. Let me just, I think I have it. Let me see if I have it open over here. No, I don't have it open. Sorry, I'm trying to open. Let me close that. Okay, I didn't keep it open. Let me just see. Do I have it here? All right, I'm gonna have to go grab it from my file. Unless I didn't put it here. Okay, I don't know why I closed it, but let me go get it. Okay, I'll go get it from my file. Just a little diagram of e to the x, graphs of e to the x compared to graphs of the polynomial. So let me just go get it. Okay, I'll find it in a second. Okay, here it is. Okay, I'm just going to copy this. All right, let me pull it into here. All right, let me just get rid of this. Okay. All right, let me just put it right here. Okay, so here it is. All right. So the red graph is e to the x. Okay, so the red, this is e to the x. And then we have for the blue, this one is, we would call this one, let's say P1, the first polynomial. The first polynomial is just the tangent line. And we're talking about at x equals 0, only at x equals 0 right here. Here's 0. Okay, so all of these are going to go through, all the p's are going to go through 0, 1. E to the x goes to 0, 1. Now you see what kind of fit we have. All right, it's a pretty good fit if we just draw a small circle. All right, then it's a pretty good fit. But we can't draw a big circle because then it starts to go off. All right. Okay, so this one, this is P2. In other words, here's the polynomial, 2 terms. You see, we can draw a bigger circle. The fit is better for, I'd say just visually, I can draw a bigger circle there. It looks like a nice fit for quite a while, right? Much bigger than that one. All right, and now here, this one is P3, 3 polynomial of degree 3. That's the blue one, and so the blue one is P3. And look at the fit. It's really very nice for a long time. It's a very good fit for quite a distance to the right and left of 0. All right, you have a good fit here. And then it goes off. You see how it goes off? Here's red, here's blue. It goes off when we go away. So could we get a polynomial that's a good fit for all of e to the x? Well, you have an exact fit if you take an infinite polynomial. All right, so that's called the Taylor series. So that's really why we started learning about series. One of the main applications is finding a series that approximates a function like y equals e to the x, which doesn't have a convenient formula like a polynomial. So if we take e to the x is basically equal to an infinite polynomial. All right, and that infinite polynomial is called the Taylor series. All right, so we'll stop here. We'll look at some more. We'll look at it some more tomorrow. Okay, let's see. Any other questions? Okay. All right. So don't forget to do the homework. You have a question? Okay. All right, so don't forget to do your homework. And we'll meet again tomorrow. Let's see. Yeah, do you have a question? Okay.